Assalamualaikum. So this presentation is about epidemic routing protocol. Okay, so first of all, these are the group member, which is Muhammad Farish, Alif Hazwan, Muhammad Shafiq, Olivia Wena, and me, Siti Masar. Right, so in this project, we were assigned to improve our proposed improvement on epidemic routing protocol. So epidemic routing protocol is a flooding-based protocol, and it is a class of routing algorithm that is very useful for a network that the conventional end-to-end communication are not accessible, or when the traditional routing algorithm protocols are not efficient. Like for example, when the network topology is constantly changing. Okay, although this this protocol are good, but these protocol are not suitable for a large network due to its high redundancy, because of there will be a lot of message exchange that will also lead to network failure.
Next, explanation for proposed algorithm. This is a Java code snippet that appears to be part of a class named improve epidemic router, which extend epidemic router. And then this class has two private variables, which is buffer size and all message. For the buffer size is an integer that represents the size of a buffer, and for the all message is a linked list that store message objects. And then a constructor that takes a setting object as a parameter. It's called the parent class constructor with the setting object and set buffer size to the integer value of buffer size in the setting object. And then for the override and update methods, it first calls the update methods of the parent class. The rest of the method contains logic for handling message transfer. And then for the receive message methods, it takes a message object as a parameter. If the size of the current buffer plus the size of the message is greater than the buffer size, it's called the remove all message method. Then it's called the store method with the message object. And then for the remove all message method, it removes the first message from the buffer and decreases the current buffer size by the size of the removed message. For the store method, it adds the message object to the end of the buffer and increases the current buffer size by the size of the message.
Assalamualaikum and good day to everyone. My name is Muhammad Ifazam bin Osman with the metric number of 80063. So today I'll be presenting my part of the group project, which is to explain the proposed routing with the correct flowchart. Okay, as you can see with our flowchart, it just starts with a similar flowchart as in like every coding it's ever seen lah. So it starts with the to choose protocol. This time it is our own protocol, which we made with our own coding, just as requested by the question. And then the protocol will modify the Java file according to the coding, what it wants, like delay time and everything like that. And then also it from the Java file, it modifies the size of the buffer, which in this case we use 10 only, because that is the standard one to be used. And then it chooses the scenario. This is automated by the one machine, and then it compiles it and then runs the coding as usual. And then the output is then compared directly between the current coding or current protocol and the previous one. With this, we can make our own graph, as explained later in the experimental result. I think that's it for my part, because that is just how the flowchart goes. So thank you and assalamualaikum.
Next is the experimental result. The total number of messages delivered divided by the total number of messages created in the network is the definition of message delivery probability. This figure shows that Epidemic performs poorly in simulation with any number of nodes. The enhanced pandemic you suggested works better in the simulation for every node. The delivery probability drops as the number of nodes in the network rises. This is due to the fact that many messages will be copied and sent to other nodes, which might lead to buffer overflow and the dropping of message before they reach their intended nodes. Next is the experimental result for overhead ratio. Wireless delay-tolerant networks allow nodes to communicate with each other continuously. Multiple copies of created message define the overhead ratio. The impact of copy numbers on transmissions and bandwidth consumption is highlighted by this bandwidth efficiency ratio. Since less bandwidth is needed to convey message, the lower the number, the better. Our enhanced epidemic routing protocol outperforms the original epidemic routing protocols in terms of overhead ratio, as you see in the figure. A better pandemic utilized less bandwidth and produced fewer copies of each message. Epidemic performs the poorest as predicted, since nodes duplicate messages a lot. The message is copied and sent to the neighbor when a node encounters them, and they don't have a message. In epidemic, no further parameter checking is carried out.
For area of improvement, we have three area of improvement. First is make the routing scheme optimal. The current approach is attempting to provide deliverable messages first, followed by an attempt to deliver all messages across all connections. By using a more effective routing strategy, such as attempting to transmit messages exclusively to nodes that are closer to the destination or that have a higher chance of successfully delivering the message, we might be able to increase performance. Second is apply parallelization. By splitting up the message transfer process into multiple threads, you may be able to increase performance if one simulator allows it. This could be providing some sort of parallelization or transferring messages concurrently utilizing multiple threads. And the last one is put message buffering into practice. This router does not currently have message buffering in place. To hold messages that are being transferred or are waiting to be transferred, you can think about implementing a buffer. By lowering the quantity of messages that must be transferred at any one time, this may enhance performance.